Welcome. In this session in linear data analysis, we'll explore the covariance between two data vectors, and we'll gather covariances into a matrix. Let's begin by recalling variance. So the variance of a data vector is the dot product of its difference vector divided by 1 minus the number of entries. So we take the squared norm of the difference vector and we divide it by the degrees of freedom in the data. The covariance, it has a similar definition. So the covariance of two data vectors is simply 1 over the degrees of freedom times the dot product of the difference vectors. And we could write that in another way. We could write that as 1 over m minus 1, and we could write that as d1 transpose d2. And whether we write it in the dot product form or in the transpose form, we can immediately see that this is a symmetric function. If I take the covariance of x1, x2, that's the same as taking the covariance of x2, x1. So there's a symmetry that's present. Let's explore what that means for this data set. So previously, we figured out what the variances were for the data. Now the question is, what's the covariance? So here, the covariance is 1 over m minus 1. And let's use the transpose form. Let's say that this is d1 transpose d2, and that will be 1 over here, m is 1, 2, 3, m minus 1 is 2, and then what I'll do is I'll put these into a row and then put these into a vector. And now when I do that multiplication, that's 1/2 of 0 minus 2, 2, so minus 2. So the covariance of these data is minus 1. And this negative simply means that there's a deep sense in which these data are, they're not just covarying, they're not covarying by very much, but there is some sense in which there's a negative correlation. And we can see that negative correlation coming out in the second entry. Now, what does this mean in general? Well, suppose we have so let's consider a design matrix. We'll get into design matrices later on, but for now we'll represent this as a capital X. And suppose that we're given a number of data vectors. So we have data vector 1, data vector 2, and so on. And then let's suppose that we have n of these data vectors, and each one of them has m entries. So this is going to be an m by n matrix. And the question is, what are the covariances? So we could write the covariances as in a detailed manner. So the covariance of all of the data together is, well, we could write this as a matrix. And this first entry would be d1. So we could say d1 dot d1. Let's say d1 transpose d1. And then the second, the entry 2, 2 will be the variance of the second vector. So that will be d2 transpose d2. Now, how does data 1 covary from data 2? Well, that would be entry 1, 2 of this matrix. So that would be d1 transpose d2. And then how does entry 2 vary from entry 1? Well, we could write it in either way. Let's write entry 2, 1 using 2 and 1. So that would be d2 transpose d1. And as I continue on, eventually I'll have represented all of the data vectors that were given using their differences. And then what will the first row end at? Well, this is D1 transpose, D1 transpose. So this will be how D1 covaries from data vector n. And as we carry down this column, this will be how data vector n covaries from data vector 1. And when I see these, what I can do is I can start to observe a pattern. And this looks as though it's a product of two things to me. So as I explore, let's concentrate on this row. So that row, 1 over m minus 1, almost forgot. So that is going to equal 1 over m minus 1. And now, let's try representing this. So the first entry is D1 transpose. And what has D1 transpose been multiplied by? Well, it's been multiplied by D1. And then we can see, we've run out of entries. So we can't follow. What is entry 1, 2? Well, that is D1 transpose times D2. And so on until it's entry Dn. So we've now computed the first row of the covariance matrix. How do I compute the second row? Well, that would be entry 2, 1 that is D2 transpose times D1, D2 transpose times D2, and so on. And so our pattern is that this covariance is a product of this matrix times this matrix. What does this look like for our particular example? Well, we'll concentrate just on this upper corner. So the covariance of our design matrix for these simple data will be, so this will be the covariance, this will be the variance of 1, which is 4. This will be the variance of 2, which is 1. This will be the covariance of 1, 2. This will be the covariance of 2, 1. And I note in passing that this is a symmetric matrix, and it's also positive definite. Now, coming back to this general case, what we have here is, suppose that we represent this as a matrix D. So our covariance of our design matrix is 1 over m minus 1 times, if this is the difference matrix, so this matrix is, each column is a difference vector. Each difference vector is the difference between a data vector and its mean. So we can compute these, is that the covariance is, this matrix is D. So what does that make this matrix? Yeah, it's D transpose. So by construction, this is symmetric. And when it has this form, we know one of two things will happen. So this means, that means that the covariance matrix of any design matrix has to be symmetric and positive semi-definite. And a fact, so a fact is something that is true and we're not going to prove it. Fact is if the difference matrices, if the difference vectors are linearly independent, then D is full rank, and that means that the covariance matrix is symmetric, positive, definite. So when does this happen? This happens when, from statistics, the covariance matrix is symmetric, positive, definite, if and only if these x vectors are statistically independent. And that is a very useful observation, that if and only the covariance matrix is positive definite, if and only if the data have some very useful statistical properties. What have we learned in this lecture? Well, we're now able to relate eigenvalues to the quadratic form, or if you wish, to the energy term, depending on which words you want to use. We're able to find a positive definite matrix from a full rank matrix, and from a non-full rank matrix we can find a positive semi-definite matrix. We now know how to compute the mean and variance of a data vector, and we can formulate the covariance matrix of data vectors and discover that if the data are statistically independent, that this gives us a symmetric positive definite matrix.